how is that? Just do one question, that's it? Oh,
No, just one. You just choose one question.
and I can choose all questions.
I think if Ben
For
was still in the class,
as long as I,
because I always
do his requirements.
You gotta do it with no help, no nothing. You gotta do it on the board.
All you wanna try?
Yeah.
So let's say I do it. It's wrong. Can I fix it
Yeah,
on
you
the
literally
spot?
redo it on the spot.
And you said wrong, please, that's right. It's like, okay, twice. Oh,
last week.
that's awesome.
Yeah, I was thinking there's no point in doing it now.
Like you just
You'll make it out.
I'll do it. Cause I have 3 more books.
Okay, it's taking a while.
Yeah. Even if I guess.
that night question.
I don't even know how to look at it actually.
Come on, come on.
But I think part of the reason I didn't do so well
Memorize it.
because we didn't try chemistry, I didn't try chemistry, so we're just kind of like.
But then
Okay, now the thinking slowly.
I think that's what he's trying to do.
No, it always seems like it's fun to work with friends, but then it just doesn't work out.
Yeah. I should have done that. Before this midterm exam. Oh,
Oh, okay.
We all want it.
Oh,
It
wow.
has to be done.
And that's not cool.
That's the bad thing about living in home, I can always, I can turn on my game system, I can turn on my TV, I can do so many different things.
You know, he knows how to do all of it. He's like,
If it gets late, I'll just scale it and see or something.
He's
That
good.
won't
That won't
make it bounce off
I'm
the
not
wall,
going
but
to
it's gonna give you a little.
just too much. Or
but I think that he does something like
yeah, it's your heart. Or you're not.
Okay, so my name is Veronica, I know what people don't know. We're gonna go with the review with the exam that Professor Alice put online and with me as well. We'll start with the groups. It's a proof of exam 3, April 17, 2014, and it's problem 19. Okay, so the proof is having.
You might have to turn that off. I'm pretty sure you do see it. No, like the screen, like what she said.
You press the little power button. That should work.
Yeah. You
I
should
thought you had
see
to
it.
press with one of the pens, that's how it used to be.
This is not one of these things I know how to use.
It's just food. We had this in school.
Yeah.
My high school.
Yeah. They take a while to make things show. Yeah, it's going now.
I'm not as smart as I get. We can say a little.
No, you're smart.
Oh, it's funny, no, these things are really old, they just have old types of screens.
Okay, so we have M, three integers. And we say that, okay.
You have to do marker. Left side, you have to click on the marker
Yeah.
and then go for it.
Oh, okay.
Okay.
That's selected.
Are we still gonna do it on the board?
Oh, you have the movement tool selected still. See that, the crosshair? Under the keyboard icon on the left, I think you have,
We like this.
all the way at the bottom, it looks like you have one you still highlighted. Oh, oopsie, you wanna do that again? Orient. Oh, you have to calibrate it.
Oh, jeez.
Oops.
Roundness.
Yeah, just tap all the corners. I guess we may as well calibrate it.
This is one of the reasons why I shouldn't use it. Okay,
Oh, that was
so
a good
once again, having that.
Put the marker down and then pick it up. No, on the blue, pick up green. Try to pick up green. Dark black, yeah. See if that helps.
Okay, there it is. Sensitive.
Having M&M's, we have integer. And we have if n plus n is 1 is even, then n is on and n is on.
I'm sorry. 1 second.
It's in 117. So, in what kind of proving techniques would you use to prove that, knowing that m and n are integers, how would you prove this?
Wait, what's the
The type of proof?
Yeah, you can have direct proof, contrapositive, contradiction, proof by cases.
Type, maybe.
Okay, so if you go with this as a direct proof, how would that go? So you would assume m and n are integers, and then you assume that m plus n plus 1 is even. Could you actually conclude based on that in some way after manipulation that m is odd and n is odd? Yeah, it would be kind of hard. So the second way is to do the contrapositive proof. So how is that one going? What do you assume?
And is even.
Mm-hmm. So that and even integers. So then we know, then we can write n as let's say 2k and n as 2l, such that l and k are also integers, right? So what do we know now? Since the contrapositive proof, we are trying to prove that m plus n plus 1 is odd, right? So if we have m plus n plus 1, so then we substitute back what we assume that m and n would be. So that is 2k plus 2l plus 1. And how based on that do we conclude that this is actually odd? Mm-hmm.
Do you factor the 2 from the 2k plus the 2l, so then it's like 2 an integer, or 2 times an integer plus 1 times n.
Yeah. Okay, then we can either read that or no, Professor Alex would probably want to say that k let say c equals k plus l. Then we have that the summation equals 2c plus 1, and therefore we have So then we have Mm. The next thing we can do is a proof about functions. That one is the same exam. It's problem 17. So we have this result. Then 3. 17, 2014. So here we have that a one-to-one function. So we know that we have a one-to-one function from A to B. Satisfying.
What is that inside that?
F of A1 does not equals F of A2.
Okay.
But- So here we have, they are giving us the information that the function is one-to-one. And then it tells us that it satisfies another condition, that f of a1 does not equal a of f2, and we have to prove, and then we know that a1 does not equal a2. And we're supposed to be proving, that's one the best thing. Then we have to prove G. This is a composite function. Is going to how do we start this? Oh, Professor Allen is giving you another little thing. Tells us that you have to let A1, A2 be element A for A Simpson. And A1 does not equal A2.
Oh, yes.
Okay. So we start with a second problem. Here's the problem description. Here what you're supposed to be proving. No, that's what I just asked if they are correct. Okay, either way, so how would we start this proof?
Like the type of proof, the right spot.
They are telling us that the function is one-to-one. So what do we know? Since it's one-to-one, it has to satisfy this condition, right? Since by our assumption, a1 doesn't equal to a2. So what does it mean for a function to be one-to-one?
Output. No outputs have the same. Unique outputs.
So if, for example, let's say your a1 is 3 and your a2 is 4, if you plug into the function, the final answer, that say b is the output, will not be the same for both of them. So So since you assume that A1 and A2 is different, you know that since it's 1 to 1, your since the relation is 1 to 1, f of A1 will not equal to f of A2. So what would be the next step? What do we know? We are trying to prove that the composite function g of f of x. So what do we know about this f of a1 and f of a2 for that composite function? We know that these values will be the domain for the composite function.
Were we given that G is 1 to 1 as well?
That's what we are trying to prove. So that has to be our conclusion.
I thought we're proving G of F. Right.
We don't know anything. No.
Yeah, it's a
We know that
function.
G, yeah.
G as well?
Yeah.
Okay.
Okay, so knowing that, what do we know? Since G is 1 to 1, 2, and this is the domain for G.
Uh-huh. You can plug it in for G.
Yeah, so that tells us, so it's sort of like the same, here we have the same assumption for F, that's our assumption for F. Here we conclude this assumption for G. So therefore we know that this has to be in D. So we know then A1 are elements of the set B. But since we know that the G is 1 to 1, G is 1 to 1, we know that G of f of A1 will not equal to G of f A2. You would think that this is the end of the proof because you would think that just proved it, but still you have to show that the composite function is actually what you're getting here. So what is the definition of the composite function?
Just have the definition right
It is. But so first you would have to write it in the above form. So you have to write it in this form. G of f of A1 is the same as writing G of f of A1. Okay? The same would follow for G of f of A2. And since we know they are not equal to each other, A1 is not equal G of A2 because prove this. And if you guys didn't prove this part, it would be happening. Even though you know it's the same thing, you still have to show that by definition they are really the same. Okay, so what did we start with something else? And you guys went over series, right? So, okay, so this week, write down the initial term and common ratio of the series that you see. So the initial term so what is the initial term?
Is it I sub 0?
Do you have I sub 0? The series starts at 3.
So it's initial term at 3?
It's all, the initial term is always what you see I to start with. So if it's I equals to 0, the initial term is 0. If it's 100, the initial term is 100. So always pay attention what this little number here says. So if the initial term should start at 3, you have the 2 times 4 power 3 over 3 cubed. So that's that.
Should I or not? Maybe not instantly. I was thinking about it for a minute.
I always like common ratio. It's a little more tricky.
Common ratio.
It's not a very good number.
It's usually, it's a term that will be repeating every term you have. For master 30 or MS 1, that's in 117. That's the common ratio is the term that repeats. So which is the term that you're bringing to the power? We can rewrite the series to be something like this. A plus 3, 2 times with that look more familiar. So what's that common ratio then? The term that repeats, right?
Thirds, yeah. It's one of those moments where I feel like it's a trick question or something. Even though it's right in my face. It can't be
But
right.
just wait till you have 5 answers for that particular one. And they sort of all look right. So what is the sum then?
See,
What was for this?
No.
straight up no. Well, if it goes on infinitely, how?
I mean, there's only a arithmetic
Oh, that's right,
one
you're right.
that goes like And then you have a geometric one, like the one you have on the example. So what is this on?
Oh, this is 1 over 1 minus r.
Oh yes, that's what it is.
Sorry. But our r is greater than 1.
Mhm. So we can't have it because then it will be negative then.
I think what he was saying is it's to infinity.
Mhm.
It just keeps growing.
Yeah, because since r is greater than 1, it's growing and growing and growing.
Oh, okay.
I mean, you probably will never have this question, but you may have something similar. So what about if the formula for the series is something like this? So the formula would be 2 times 3 over 4 1 minus 3 over 4. And would that be on? That is a trick question.
Oh, boy.
In some ways it would be convenient, but in other ways. What is trick that it started to? All our series started with 1, right?
You subtract the first term.
Mm-hmm. Then you can simplify it, you can leave it as it is. If you have multiple chunks question, that's probably when you simplify it. You can understand what it is like that.
Oh, I mean, I know, I just don't really know what that example is supposed to show.
Oh, wait. This falls from the formula.
Oh,
That's
okay.
something you guys have to memorize, derive.
Oh, that one.
I mean, you may not necessarily have enough time to derive, so I propose to memorize.
Okay.
You can be ambitious and derive. I mean, you probably should stay on stages now. Do you have any questions? No? Okay. I'm serious question. This is from 2009 exam. that one is because we are supposed to be recording this one and you can record it.
Thank you.
Okay, also, no, they give you answers.
No, I changed it.
I think he knew that this is not a classroom. So which of the following gives a recursive definition for an equals 4n plus 3 or 4n where n is a natural number? On the exam it is enough to guess. However, there may be a question where you actually have to prove it. So how would you there are a lot of methods to do it. There are more time consuming methods, less time consuming methods. One time consuming method would be like, okay, they give me the I naught. They give me I naught, then I can probably compute first few terms compared to the first few terms that we'll be getting here. So it's going to be going from 1, 2, 3, 4, 5. But you probably shouldn't do it like that. So the method to do it, they give us what a and s. So what we're going to do, we're going to be substituting the a and back. So we know for a, our a n will be 2, and then we substitute for n minus 1 plus 1 plus 3. Plus 3 plus 1. It should give us back what we're getting. So that gives us a n minus 1 plus 6 plus 7. So that gives us 8 n minus a plus 7 plus 4 n minus 1. Did it give us what? Oh, 8 n. Did it give us what we had in the beginning? No. So a is not the answer. So for the same, we do it.
Oh, okay, so just exhaust all of them. Okay,
Yeah.
that's fine.
So for C, we can have a n equals, we have 4 n minus 2 plus 3 plus n. 4 n minus a plus 3 plus 8. 8 will cancel. We arrive at the right answer. So we know our answer is C. And we don't check more. We could have, but we already got the answer. So the whole idea with this thing, when you have that recursive definition, you just for n that you have is 4n plus 3, you replace the n with whatever they give you, n minus 2, or n minus 1 and n minus 2. Or you can just do few terms and that would work too. But since first two terms will be the same for all of them, would take a lot of time.
So you're mentioning there might be a case of proving it. I mean, would that kind of answer suffice for it, or I guess what would the question even be asking at that point if you had to prove it?
It would have to, you would be deriving this.
Oh, okay.
So there, it would be asking you what is the recursive definition or to prove the recursive definition.
Oh, okay.
So
what
those are usually like 2 to the power of n plus 3 or 3 to the power of n. So I'm not really sure if you guys did induction already.
It's gonna be on the test, yeah.
Yeah. So that's definitely something that
Wait, induction's on the test?
Induction, yeah. But that's strong.
I don't.
I thought it was 7.2.
That is 7.2.
That's 7.3.
There's
Strong
induction
induction.
7.2.
Oh, because there is a strong induction
Then regular.
and the regular or the weak induction.
Yeah, I don't think I know
we-
anything about
we did
inductions.
strong induction.
Yeah.
We're okay.
Oh, yeah, no.
Do you guys want me to go over an induction problem?
Oh, yeah.
Okay, then we'll go over induction. I don't have any problems on the induction here, but I will make something.
Old.
7.3 and 7.4 are induction.
Okay,
That's
so
7.2. That's 7.2.
7.2 is recursive algorithm.
Oh, wait. So maybe there is no induction. Maybe you are right.
So,
Yeah.
no induction?
No, there's no induction.
I thought there was.
Don't worry, I'll be able to find one.
well, you know, if
Yeah.
there's any extra,
That's true.
if there's any extra time, maybe we can go.
Strong induction is what I hate.
Oh, yeah. One of those was
It will be there. It will not miss you.
I'd be better off just to.
Can we go over recursive algorithm problems?
Do you guys have an exam? Because Professor Alex didn't.
Yeah, it's gonna be on there.
Yeah.
7.2.
We could do homework from last time.
Oh, yeah, do you have any problem?
Yeah, I mean, everybody gets access to it.
So I will do one problem in between before you guys get the problem. So what do we have? Another one. We have some algorithms. Okay, there is some function. The other person who gets knows how to do it because it's easy. This is the floor and ceiling function. How do they work? This problem.
Yes, that'd be great.
Okay, so if we put 5 here, what do we gonna get? 5/2 or what is that gonna give us? And we put, so what do we have? We have, you rewrite this as f of g of 5, right? So what is our g of 5? G of 5 will be ceiling 5 minus 2 times 5 over 3. What that gives us? That gives us ceiling of negative 5 over 3. So that is what? Negative 1 2/3. Since the ceiling, we bring it up to the closest number. So that will be negative 1. So now what is f of 1? Negative 1. Is negative 1 over 2. So what's that going to be? Okay, because since it's the ceiling of a negative number, if it was the ceiling of 1 over 2, I mean the floor of 1, that would be 0.
Yeah, right.
And then, because it's negative, it sort of becomes that.
Oh, no, yeah, I understand it.
Okay. But just so it becomes negative. Okay, so there is a problem on the exam of 2011 for the question you did ask. Kind of long. Okay, I will let it know. So it's going to be binary search.
Wait, we didn't do binary search trees.
You get it?
We didn't do it yet.
No, we just did binary relations, you're
Wait. Binary relations or binary search?
right. No, relation, I know search came up like once.
What is she gonna write? Sorry. What-
Search.
The binary search.
We didn't do search, right?
You're sure?
I mean,
If it's on this page, it might be fairly.
yeah,
Oh, it's
that's
fine,
what I'm thinking too. Because this is one, I mean, Professor Alice pointed a few of these kind of problems.
He said chapter 4 is not on there. So let me check it out. Do you know, did we go over binary search?
Okay, did you guys go over any bubble search or anything?
No.
I know what it is, but we didn't do anything like that, no.
Okay, there is another question. So, okay, so the question is, a recursive algorithm for computing the Fibonacci number is as follows, and this is part of the minute. This one will be on because Professor Alice pointed that one specifically.
Okay.
I mean, that's what you can I don't know. I mean, this question may not necessarily happen on your exam on Tuesday, but it's definitely going to be on the final. And it's probably going to be the same question because I got that question on my exam.
There's something wrong with going over.
So this is where the procedure starts, it ends here. And this is the question. How many times is Fibonacci 2 called in order to compute Fibonacci 6? How do we compute that? So in our case, n is 6. So n equals 6. And we are interested in how many times they will be using Fibonacci 2. So when n is 0, we just return 0. So Fibonacci was used 0 times. How did you compute 1?
You said it, not me.
I mean, I'm not.
Okay.
Wait, how does it return one?
I don't know.
Oh,
I'm not sure if it's right or not. I'm just.
zero factorial is one. Right?
No, but you will, if n is 0, you will never use Fibonacci of 2 because for Fibonacci of 2 of 0 and 1, you get that they give you then f of f of 0, 0, and f of 1 be 1. And the Fibonacci sequence goes 0, 1, 1, 2, 3, 5, 8. So probably what is so it's f of 2 is 1. Is 2. 4 is 3. So to compute 8, how many times will be calling this one to compute this one? If you write it down, f of 6 will be f of 5 plus f of 4. And that can be written as f gives us 2 after 4. 7 plus after 3 gives us 2 after 3 plus after 2. Gives us 3 after 3 plus 2 after 2. But to complete after 3, we still need after 2. That gives us 3 after 2 plus after 1 plus 2 after 2. That gives us 5. 2 plus 3. So 5 is the answer. In all these type of questions, that's what you guys have to do. Either you know and you guess. So this is the ABCD question, you don't want to waste time. Or you just go through it. And honestly, my advice to you, don't do wrong questions, especially on exams with professor hours. Not that. Honestly, if you don't know question, you either guess or come back and then get all of them that you're missing. And if it says 20 minutes for that part, no more than 20 minutes. That's one good advice. So you guys know where I got that from. You just substitute back where it's supposed to be. Okay, no switches. Oh, so we can use the function. You guys covered the, where is the O of something? Oh, I guess they don't like it. I don't like it either.
I hate it so much I want to. I got how it should turn out, but I really getting there. You know, Zygo shows a graph or something? Yeah, it really looks good.
So what does this O stands for? And later on you will realize that O always stands for the error, which is the highest term you can type in the function. How can we differently write this log, this whole term? Where is this magical property of logs? It moves powers, it adds things together, multiplies things.
The coefficient can get thrown in.
Mm-hmm. Right? Does any of these answers look similar to what this became?
That's one of those things.
Does that make sense?
So it's gotta be the same?
Yeah.
Does it have to be higher? Is this the one that's
No.
higher, or is it have to be the
It
same?
can be equal or higher. And since you have equal in this case,
Uh-huh.
that's what it is.
Oh.
Oh, we're just using log rules then. Okay.
Mm-hmm.
So what if it was like theta or like omega?
Yeah.
How would that differ?
Okay, so there is a rule for that. Let me see, remember. omega and beta rule, they have a rule. One is less or equal to absolute value. You guys have your notes. Wait, this is the button.
Which one's the one that goes to the horseshoe?
Oh my god.
I think that's lower.
Yeah, like the bounding function. But there's a formula and I don't remember that. That's what you didn't even remember. I don't remember the one. Yeah, the O is the higher bound, omega is the lower one.
What's theta?
Just all of them. No pun intended.
Okay, so the big O function big O. So we say that the function is all with geometry. Here it is C. Okay. So then put times. Oh, we will make and we will get it. And then for omega, it is that one. You guys should know this.
Yes, it's on.
Okay, yeah, and then I have omega, so we say that it is omega. So after that, and then you have the data with these little thingies that would be both O and omega at the same time. So you have that is so see there is this oh this is magic. So it pretty much tells you that you can have two bounds of the function. Always only tells you the upper bound, omega tells you the lower bound, and this magical thing, this extreme. Tells you both of the bounds. Now I'm going to do an example. find that. Okay, so we're gonna find the O of length So what is the error? This is still the error one. So what is the highest power of this whole function? Hmm? Mhm. So for big O, we have this definition that there exists C and K. So we need to find C and K that satisfy this definition. How do we solve it?
The highest term first.
Here we have it a little bit complicated because we would say, okay, it's x squared. Do we show you that it's x squared? If you go through a lot of problems, you probably gonna know this is x squared. But how would we compute it otherwise? Since we have logarithm, can we bound the logarithm? So you want that for I don't know, k equal to 1. We will have from x squared plus 1 is equal to kind of equal to almost 2 log x, and that can be bounded by then it's just bounded by x. because if we plug in 1 for x here, we have logarithm of 2 that is approximately 0.63. So that is less than 1. A linear function grows faster than the logarithm function, so we know it's always bounded by the x. So we have the logarithm function and the x function. And this is the logarithm function. So we know that x is always bounded by logarithm. So now we can rewrite the function we have as f of x is bounded by x plus 1, x plus 3, x squared. Then we multiply it out. And then it equals x squared plus x plus 3, 4 x squared plus x, and we can multiply 5x squared. And then your c's, so c equals 5, as the function is of and this is something you're probably going to have on the exam.
Did you simplify from adding the coefficients of like the x's? Even though they're not the same power?
I mean, because since you know that x squared is again growing faster than x, you would just
Okay,
talk
you can just-
about 1, yeah.
Another way to look at it, you do right side is 4x squared plus x squared, where you know that x squared is greater than x.
Okay, yeah, we should probably do that because I think that's not going to know what I'm getting from. This is probably an example you're going to have an exam. And it's not going to be harder than that. But it's definitely be bounding and it probably will have a logarithm. Okay. Okay, do you guys do any more proofs? Now you can pick.
The only things I suck at are proofs, so yeah, I think it's well.
I was in it. Tickets in there. I was in.
Okay, so what do we assume here? This is all up to you. I'm just going to be writing. Yeah, we'll wait for you so you can think.
I can think for hours, it's still confused.
What I would advise is that what you have, just memorize this scheme for the proofs.
Does this have to be really formal? Can I look at cheat?
What what Professor Ellis is mentioning, like you actually, the way the points go, it's for formulation of this assumption, of the use of this assumption, or since it was by definition that you have that this is by definition. Like my proofs are probably too long,
Okay.
but although the ones I wrote for you is 9. But in general, mine are too long. But with Professor Ellis, it's easier to have it too long because he doesn't say point out, than too short and miss the point, even though got it right. Yeah. So, what are we going to do with this problem? What kind of proof are we going to use?
Can we use a direct?
Mm-hmm. Why?
You said well, 2k plus 1, right? Whatever the general.
Why? Because this power is cubed.
Okay.
And to prove it otherwise, you would have to take a cube root of something. And how do you know what is the cube root of some number? So that's the only reason why it's there. It is, I mean. So what do we assume?
This one, the n is even.
So that and we even. Okay. So what comes out from that fact?
Then n is equal to 2 times k, with k as some integer.
Mm-hmm.
Let's just see the one. One second.
Okay. What's next?
Then we plug in k into
And then we have n cubed plus 1 equals, yeah, we plug it in. This is supposed to be
The one thing I was never wrong.
okay.
It's not touch based, that's why. Oh, it is something like us.
How
It's stuck in the drawing.
do you even appear? This thing is magic, right? So okay. We know k is an integer. And we know what do we know?
We might have the 2 from the
Mhm.
so k cubed equals 1, and then k cubed is an integer, so that's like
No.
cubes plus 1.
So what do we have to prove? If you guys have to prove it and it's even, then n squared minus 1 is odd. That would be pretty much the same thing, right? Or do you have to prove that n squared is odd, then n is even? How would you prove that then?
Just flip them around, couldn't you?
Mm-hmm. Then you do it by contrapositive, right? Should we do it?
Sure. Why not?
And with Professor Ellis, you have to write that you're doing it using direct proof, concept positive, or contradiction. Because you may actually get points out from that, writing these proof this.
Yeah, he does. I know.
Just making sure because I never do it unless it's induction. Yeah, so what kind of proving technique will we be using here?
Controversy?
Which one?
Say contrapositive.
Oh, yeah.
Okay.
I didn't hear it. That's
Oh,
why.
oh,
I'm
that's
sorry.
So you can say proof by contrapositive.
Yeah.
Okay.
Yeah, I didn't hear it. That's why I asked.
Oh, okay.
Okay, so what do we assume?
Contraposition.
Oh, let n be even? I'm sorry, odd.
Mm-hmm. Then, so what do we know next? Next, so we expand. We have 4k squared plus 4k plus 1 minus 1. One's cancelled. What do we do next?
We're gonna put out a 2.
Mm-hmm. 2 what?
2K?
Do we have to add 2k?
Oh,
Because then you would have 2k plus some c, and you would still have k to be an integer and c to be an integer. So you have kind of like 2 integers, but still doesn't give you anything. So now, like, k squared plus k. Ooh. See?
Wouldn't it be 2k squared plus 2k?
Oh, yeah. Thank you. Definition.
You proving it odd?
No, because we were doing by contrapositive.
So do we assume if n?
So we were assuming that n is odd,
Yeah.
and then we are proving that m is an even. Because it's odd here,
Okay.
so we are
Doing
proving
the opposite of
opposite.
both. Okay.
Now we can prove f that goes like this. The equation 2x squared plus y squared equals 14 has no positive integer solutions.
Should we write that down? Equation?
Oh, we will, but I'm just giving you that so you can think.
This is on the last exam.
Did you ever like them?
So this is on the last exam. We like have to prove it.
Do you guys know how to prove it?
Must have been the one I didn't get.
I don't know how to prove it.
I proved it away, he didn't want it to be proved, but he still gave me the points.
It's the equation then.
Okay. Two. He didn't like that answer, but that wasn't there. maximization.
So, isn't it even plus I?
And this one is 2x squared plus y squared is 14. Here you will be doing something else. You for a second will be assuming that the x squared is 0. Whoa. I didn't know what I'm doing with my hands. You will be assuming that 2x squared is 0 for a second and how big your y can be. So, if x is 0, and this is not really part of your proof because then you assume by the downloads generally x is at most 3 or 4 and y is at most 5. I don't know. That's what you're calculating. So this is not really part of your proof, this part. We are just computing the bound of the y squared. Then,
Just call it square.
yeah,
Side work is what's
then y squared equals 14. And that gives us that since both of them are integers, has no integer solution. So what is it the most? If we take square root of 14, what do we get? We get 3 point something. So y is at most 3. So y is between 0 and 3. And then if y is 0, then what do we get? We get 14 divided by 2. That gives us 7. Square root of 7 is 2 point something. So then x is at most 2. So based on this calculation that you may include may not, you assume that without loss of generality, that's how you shortcut it, so you don't have to write it down. Include generality. Assume that x is equal to and y. And right now, it's pretty much with this assumption, this becomes a proof by cases. Where you check, okay, that I have x be 0. What do we get? Can we have any solution? So we can have a table here. So we have 2. We have x. We have 0, 0, this is becomes 0, so it can be 0. 0, 1, 2, 3, 4, 1 square. That becomes 1. This one is 0, 2, becomes 4. 0, 3, because it can the highest be 3. U minus 3, 9. So no, that's still wrong. Now we go with x being 1. 1. X can be at most 2. So there was 2x squared, so that becomes 2. 2x squared, that becomes 2 plus 4 and 6. That becomes 2 plus 9, 11. That becomes 2 times 4 is 8. 2 times 4 is 8 plus 1 is 9. And then we have 8 plus 4 that equals 12. So we show that for all possible cases that we can have, it never equals 0.
We can do 1, 1.
Then we do 1, 1? Okay, 1, 1. So this becomes 2 plus 1, that becomes 3. How did you prove it?
I did it so that like I wrote it in a rational way. And I don't know,
I got the feeling, so it couldn't be that wrong with the background. That's
but
right.
like looking at it this way, I did not do it this way at all.
I remember I did it completely differently too. I don't remember the method, but I know that it wasn't this thing. Because I remember that mine was a page long thing. And I remember it was a lot of writing too. Yeah, but this is probably the method to use.
Will we accept the table?
Yes.
And then do we also have to do 2 when x equals 2 and y equals 3?
This assumption?
Yes.
Yes.
Did we do that?
You don't necessarily have to do this calculation, it's just there to help you know how I'm getting it, but you need this assumption.
Is there a way we can do it? I think I did it where you just assume x is even, y is even, x is even, y is odd. Just do
Or
parities.
both of them are even or odd. Yeah, we can do that way too.
I think that's what I did in that section.
Same section?
Different. I mean, because then you have a proof by case.
Yeah.
Different. What? X and Y. But then if both of them are, if both of them are even, then you don't have a case. Because you have 2 times an even number is even, and this is even too.
Oh, I see what you mean. That proves it.
You would go with, but still you're adding 2 odd numbers, no, because you're adding odds too. So yeah, you would go with the other 2, not that when the one is odd, one is even, that wouldn't work for odd and even. Although odd and odd would probably wouldn't work for even and even. Because if this one is even, the square root of even number is even. So then this gives you even, this gives you even, and this is even.
Yes.
So it wouldn't work for the even one. But it would work for the other ones.
Okay.
So proof by case even numbers, yes. We have any other proof. Okay, and then we do the function. Sequence. So suppose you have this function defined set of integers to set of real number has the rule that add n equals to n plus 3. What is the range of the function? Or is the domain first?
Domains your input, right? So that reaches to integers.
And they tell you that the possible set that your range will be the set of real numbers. So it's either the set of real numbers or the subset of real numbers. So what is the subset here? It's pretty much the question is telling you that if you plug few of these ends, what will be the output? You should pretty much see the pattern of them.
Are we given that n is bounded to something already? Or no?
No, you know that and so you know that n is an element of integers. An integer one, zero, one, two. So you can start from -2. If you plug -2, you will have -4 plus 3 is -1. So it's going to be something. -1. You plug -1, that gives you, okay, we start with -2. That gives us -1 plus 3 is -1. -1 is -2 plus 3 is 1. Then we have 0. 0 times 2 is 0 plus 3 is 3. Then we go with 1. 1 times 2 is 2 plus 3 is 5. Then we have 2. 2 times 2 is 4 plus 3. And that's 4, 3, that's 7. What kind of pattern do we see here?
It's a common difference of 2.
But what are these numbers?
Odd.
But what odd?
Integers?
And they are indeed in the set of real numbers. Because the real numbers are the numbers that encompass everything between 0 and 1 and 1 and 2. Do you have any questions?
much, right?
It's hard to ask questions.
I think we can't for Emma still one. I was recording.
This is fine, yeah.
Does he have any time complexity problems?
None that I see here.
Isn't it related to the big O?
Yeah.
Yeah.
So that's the big, yeah. So that's the x square.
Yeah, it just applies to the algorithms.
Would you like, because when we did it on in class, we had to look through the pseudocode that you gave us and then figure out what the values of M and N were. And then
Oh yeah, I have this found.
Yes, that's my next question. Permanent pseudocode?
Yeah, we can go.
Because I don't like those nor do I get them.
I mean, this is one of the problems you set up for the variance. Because it works, but make sure you have at least 7 minutes of time to do it. Because it takes a lot of time, but you need the pay for it. So we have this binary search. With x39 and this is 6 and 14, 16. Then I'll text them. Just for the publicity. So we have can we do it? So we have, you know, there is a binary cell, which is 6. Okay, so we want to know what it prints again. So in our case, the set of integers here. One, two, three, four, five, six, 7, 10, 14, 16. So we're looking for where it's going to print. So what do? First we know that I equals 1 and j equals 1. So we know that 1 is not less than 1, so it doesn't go to that. Then it's growing. Okay? So how do we go with it? Oh wait, j is now 1. And our n is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
So is the m assigned equals, that's supposed to be a floor or, bracket?
Each 4.
Okay. So you'll start the loop, begin using I, which is 1 plus 10 divided by 2.
Mm-hmm. So that's 5.
Right.
So if x, in our case, x is 9, we can replace it. So it's easier to see. If 9 is less than a n, which is a of 5. 2, 3, 4, 5, which is, here is 5. If 9 is less than 5, we do this, then our I becomes n plus 1. So that becomes 11. And our n, n. Okay, people will start doing that. I need to change like how people write. 1 n, 2. Okay. Okay. So we know our first n is 5, right? So we're gonna put it here 5. Then we know that 9 is greater than 5. That comes from here. Then I becomes 6. And j still can have it plus. So then we go, so it prints I, j, and n. That's what we have. So we go with the loop again. So we know our I and j, so that becomes 16 over 2 becomes 8. So a n is 8. So a of 8. 1, 2, 3, 4, 5, 6, 7, 8. Ooh, 9 is not greater than 10. So j becomes n. So j becomes 8. And I becomes what I was. Then go with the loop again. We add them up, we get 14 over 2 is 7. 1, 2, 3, 4, 5, 6, 7. 7 is less than 9. Then I becomes 8. And j is what j is. We go with the loop again. Yes, 16 over 2, that gives us at the 8. Then we have 1, 2, 3, 4, 5, 6, 7, 8. It's 10. 9 becomes 9 less than 10, so it goes to out. J becomes 8. And I was 8 as it was. And there we go again, and it doesn't work anymore. So that's why it's coming. Clear or not clear?
Clear. In the if statement, is 9 is greater than or equal to what is that? An N?
A of F.
Oh, A of F, okay.
And those A of N's we have here.
Okay.
Since J is equal to I on the third loop, should we stop after that?
But I was just showing you the book. So yeah, the table stops here.
So you can take our points if we were to
Yeah,
continue.
these ones you don't need anymore. Yeah, because to go with it, it has to be smaller. So this one is not fails. Fails. So pretty much what I always do, I write little numbers above, so it makes sense. But then it's very messy, so I never found a really good way of doing these. But you need some time for this because you actually have to go one by one for them. But this is binary, so you divide the interval into, so at some point you're just looking at that. Half of the numbers, that's all the numbers like before. Bubble search is a little more complicated.
It's really inefficient too.
Was the question just to like print out I, J, and M?
Yeah. I usually have an point in that. Even when you have bubble search, you will be writing you will be printing out how each sorts the numbers. So it just sorts one by one, and it goes again one by one. Any more questions? I can give you that one time. Any questions? If you have any more questions, you are free to come to ARC tomorrow at any time. We can help you guys with homework too.
That says it right now.
You know,